So we're going to start thinking about chapter 6, and chapter 6 has sections and it has subsections. I'll just give you an example with section 6.1. It's broken down into 6.1d, which is about the distribution, the sampling distribution. It has 6.1 CI, which is about the confidence interval for one proportion. And it has 6.1 HT, which would be about hypothesis tests. Now, we have not talked about hypothesis tests yet, so we're going to be skipping the HT subsections. We're just going to be focusing on the D and 6C. We're just going to be focusing on the D and CI subsections of each of the sections in chapter 6. So we're starting out, we're talking about the sampling distribution for a single proportion and approximating it using a known distribution. And so what we're going to say is that if n is large, then the standard error of p hat is equal to the square root of p times 1 minus p over n. Now, if we had done a little more of the probability chapter, chapter P, I could show you the whole proof as to where this equation came from. But we didn't do those sections this semester, so you might not understand the proof. I will put a link to the video where I do it in the description of this video in case you want to look at that. But for right now, I'm just asking you to trust me that this is the equation for the standard error. And there's this thing called the central limit theorem, which tells us that as the size of our samples increases, the distribution is going to converge more and more to a normal distribution. So what I have here across the top, this is my sample size. So if I took samples of size 1, size 10, 30, 50, and then the one that you probably can't see is 100. And then I'm looking at the different proportions. So if the true p was 0.01, this is what the distribution would look like. If p was 0.5, and if p was 0.7, that's what it would look like. And we can see that if we just get to take one sample, we get this really weird looking distribution. So if we were thinking about this with maybe weather forecasting, if we're saying, the true proportion of days that it rains is 10%, and I just get to sample one day, either it didn't rain or it did rain, and I have this weird looking distribution. If it's 50-50, rained or didn't rain, and I take a sample of size 1, well, yeah, either it didn't rain or it rained. But if I get to take a sample of size 10, I find 10 days worth. I'm like, okay, sometimes none of the 10 it rained, sometimes a couple of them it rained, I get a little bit nicer distribution. If I get to take samples of size 30, I get a nicer one, 50, and if I get to take samples of size 100, I get an even nicer distribution. So this is true as the size of the samples goes up, we get a nicer and nicer, more and more symmetric bell-shaped distribution. And the center of that distribution gets closer and closer to the true proportion. So for this one, p equal to 0.1, it's getting closer and closer to 0.1. For 0.5, it's getting closer and closer to 0.5. And for 0.7, it's getting closer and closer to 0.7. So if we have a large enough sample size, then we can say that p hat follows a normal distribution. Remember, that's how we pronounce this little tilde. It follows a normal distribution. And the way that we specify normal distributions is the mean and then the standard deviation. We get to have our standard normal with mean 0, standard deviation 1. In this case, our mean is going to be p, the true proportion, and our standard error is the square root of p times 1 minus p over n. And I said that this only works if n is large. Well, what does large mean? We're going to define it as the n times p greater than or equal to 10, and n times 1 minus p greater than or equal to 10. So you need to check those two conditions when you're doing inference this way, if you're going to use the normal distribution as your approximation of your sampling distribution. One issue is we don't know the true proportion. We're just going to take a sample, and so we're going to need to figure out what to do with that. but we'll talk about that when we get into the next section.